Hello, everyone. Thank you for joining. So this session is on AI acceleration using oneDAL and oneDNN improvements, which has been conducted on ARM CPUs from Fujitsu. I'll be presenting this session on behalf of Fujitsu Research of India and Fujitsu Group. My name is Ragesh, and I work as an engineering manager at Fujitsu Research of India. And it has been almost 12 plus years I've been working on AI frameworks and product solutions, performance optimization. And our team is focusing on ML acceleration techniques based on computational data science. And it has been almost 2 years of inception for Fujitsu Research of India. It is located in multiple locations. And our teams at FRIPL focuses on multiple range of AI framework optimizations on machine learning, deep learning, real-time data processing, data security, and generative AI and LLMs. And we are also contributing to all the major open source frameworks from our team. This is the outline of my presentation. So first, I'll give a brief overview of the AI workload optimization and what has been the recent contributions from Fujitsu on machine learning optimizations and deep learning optimizations using oneDAL and oneDNN. And then I'll have the concluding remarks in the future work. So to give a brief, as you already know, that data processing is rising. And with that, the demand for data centers is rising and the power consumption is on a rise. And with that, the current situation is that data centers have become the highest contributor to the global warming and the carbon footprint. So Fujitsu's vision is to develop an energy-efficient AI software stack to enable maximized ARM CPU performance and support green data centers. So when we zoom into the data center operations, we observe that almost 80% of the workloads are machine learning. So it's a demand that we optimize them, we make them more efficient using ARM CPUs for data centers. So this part of my presentation, I'll be covering what has been recent work by Fujitsu on machine learning optimization on ARM. So for machine learning workloads, scikit-learn library is one of the major libraries, and it supports many algorithms. And there are two options to run these algorithms, stock scikit-learn and scikit-learn Intel-X. Intel extension for scikit-learn speeds up the scikit-learn applications by a big margin, but it only supports x86 CPUs and GPUs across single and multi-node configurations. So Fujitsu's contributions has been on these fronts. The first is scikit-learn Intel-X oneDAL running on ARM. How we have ported, we'll be sharing today. Second is, now because OpenBLAS math libraries are the most important for the backend in stock and scikit-learn Intel-X, it's important that these math kernels are optimized and tuned. And third is that they should be scalable for working on ARM CPUs with the multi-threading with OpenBLAS. So continuing the legacy of open source contributions from Fujitsu, starting from 2005 when Fujitsu contributed to the Linux kernels. In 2021, Fujitsu ported oneDNN on ARM, and the most recent is Fujitsu has ported oneDAL on ARM. And this is the pull request which Fujitsu has contributed. It was merged recently. And this is the pull request which, for the first time, enables oneDAL for the reference backend selection. And with this, we were able to run oneDAL on ARM with using open source technologies only. And it has given us good performance boost for scikit-learn applications. Mentioning about oneDAL, it was part of the oneAPI ecosystem, and now it is part of the UXL Foundation. So it's important to mention about UXL, which is a group of companies formed, and Fujitsu is also as a steering committee member in the UXL Foundation. The goal of this foundation is to build multi-architecture, multi-vendor software ecosystem, which is based on open standards and it is to build the accelerated computing ecosystem for the future. Now, giving a more technical background on how this porting was conducted. So in the x86 flow for oneDAL, Intel MKL plays the most important role because that's the Intel proprietary library, and that only works on the x86 CPUs. So what Fujitsu has done is that it has contributed the open source alternatives in the OpenBLAS. And now with this flow enabled by the Fujitsu's contribution, we are now able to run OpenBLAS on ARM. So this involved finding out the open source alternatives for multiple kernels in MKL, for example, the FFTs or the random numbers or the VSLs. So this has been one of the major contributions, and it was one of the first contributions to the UXL Foundation. With this enablement of the flow, we got huge performance boost for the machine learning workloads. These are the top 2 machine learning algorithms and the speed up which we have got on the ARM platform. So we got almost 40x speed up with this porting and the SV enablement. These are just 2 algorithms, but we have seen similar results across all the machine learning algorithms which have speed up on the ARM ecosystem. If we zoom more on the MKL, what it comprises of. So it comprises of MKL DAL, which is math kernels, random number generator kernels, and the VSL kernels. So for this porting, replacement, and open source tuning, we are working on all these math kernels. And primarily for this porting methodology, 3 items were conducted. First is the open source alternatives, enablement and tuning. Second is the makefile compiler options were provided for the reference backend selection, because previously it was only depending on the MKL backend. And the third was to isolate the x86 specific code chunks and handle it with ARM. So these were the 3 changes which were primarily done. Now, as you see that OpenBLAS has a big responsibility of a important backend as an open source backend powering the machine learning on ARM. It's important that we tune it and optimize it. This is one of the first contributions on the OpenBLAS GEMM kernel. So matrix multiplication performance is very important from BLAS perspective. And in a close collaboration with the Maths Library Japan team, we have conducted a lot of tests on GEMM tuning and GEMM optimization. So this first one is updating the GEMM parameters. These parameters were already tuned for AVX and Xeon and Power CPUs, but it was not tuned for the ARM environment. So we have updated these parameters so that the cache utilization is good on the ARM ecosystem. And with this change of the parameters in GEMM, we observe that it is giving us better performance boost compared to the peak performance which is possible. So if you see, this yellow line is the SGEM peak, and this gray line is the DGEM peak possible. And with that, there is a almost 12% improvement across multiple matrix sizes which we have observed for the GEMM kernels. So these all contributions are open source. And if we go to the OpenBLAS pull request, these numbers, you will be able to find these merged pull requests in the recent past. This is the second parameter change. So the GEMM preferred size handles how the kernel efficiency would be and how the cache utilization will be. So we have modified it both for double precision and single precision. And extensive tests were conducted for this change, because how did we reach to 4 and 8? We made sure that this change is small enough not to cause any load imbalance, and it is large enough to improve the kernel efficiency. So this was the optimal point which we got on the ARM ecosystem for this GEMM kernel parameters. And this is the performance graph. It is comparing between the previous version of OpenBLAS versus this new change which has come, and it has given us good performance boost across all the matrix sizes. Now, after doing the one-core tuning, we move to the multi-core tuning of GEMM kernel. And this is the recent change which is merged into the OpenBLAS. This is the most recent one, merged 2 weeks back. So here, the goal is to implement a new thread improvement, the thread distribution improvement algorithm for a multi-threaded DGEMM performance. So this piece of code, it is also available on the OpenBLAS pull request. What this helps us is that when the matrix is distributed across threads, we want to make sure that the sum matrices don't become too thin for it to be not able to utilize the cache properly. So with this new algorithm, we are able to spread the matrices much better on the thread for the cache utilization. And this helps us for the parallel performance. And the noticeable performance gains are largely on the big matrices. And the reason is because when the matrix size are bigger, then it better spreads on. There's a lot of scope for thread improvement and thread utilization. So this is one of the improvement on the GEMM multicore. Now, after doing the GEMM math kernel optimizations, we are also looking at the multi-threading improvements. And one of the biggest bottlenecks in multi-threading performance is based on the busy waiting and spin locking, which are the primary bottlenecks which we have observed in the kernel implementations. So we are working on those improvements as well. So this pull request has improved the OpenMP locking mechanism for a refined parallel execution technique. So this diagram, this flow chart, shows now how are we implementing better, how are we better utilizing the parallel regions, critical sections, when the master lock should be released, and how do we handle the release of the master lock so that the thread distribution is much better. So this pull request has helped us to get good performance results on the GEMM performance. And this is also as per the OpenMP specifications, which are consistent with the P threads and Win32 threading backends. So with this, we have got almost 15% performance gain compared to the default performance of BLAS. And this is the last in terms of the threading optimization. This is a new algorithm which we have implemented. For the first time, we are introducing a callback mechanism in OpenBLAS. What this callback means is, if OpenBLAS has tried to use a more efficient third-party threading backend, how it can pass on the workload to that backend, get that work done more efficiently, and return the callback to the caller. So this callback is implemented in OpenBLAS, which is compatible with all the three backends, pthreads, Win32, and OpenMP. And it makes OpenBLAS more composable with the caller multi-threading. Composability means that how do we make sure that OpenBLAS plus pthreads or TBB are composable enough and they are not getting any conflict from any other threading backends. This is how MKL plus TBB has improved their performance on x86, and we are trying to do something similar for ARM using OpenBLAS plus other threading backends. So with this approach of passing the callback to the third-party backend and getting the return to the caller, we get very good performance boost. And here we are seeing how composing OpenBLAS with TBB gives us a 2.7x performance boost with this technique. So this is also open source, and there's a lot of good discussion happening in this GitHub link. You can definitely refer. And at last, for oneDAL porting on ARM, there were a few infrastructural changes which we did. So the first one was enabling scikit-learn intellects with oneDAL. Then the makefile refactoring was conducted on oneDAL. And then enabling the cross-compilation of ARM SVE on x86 CI. So how do we run the builds of oneDAL, which is ARM SVE enabled on x86? This cross-compilation was enabled. And in terms of the future work, we are working on the block size optimization, basal build support for ARM, and the algorithm and kernel tuning, which will be conducted for the machine learning workloads. So this concludes the machine learning on ARM part. Now I'll be discussing deep learning on ARM and what has been the recent Fujitsu's contributions on oneDNN and JIT kernel on ARM. So this part of the presentation is in continuation from Kawakami-san's presentation during Linaro Connect 2021, where he introduced about oneDNN enablement on ARM and the JIT advantages. So as you know that oneDNN is the DL processing library, and that's a library which is cross-platform architecture, and it helps us to dynamically execute the execution code, dynamically create the execution code for the computational kernels. And the JIT compilation technique is the technique of the compiler design where it translates the source code into the machine code at runtime rather than doing it ahead of time. This has a lot of advantages from the kernel perspective, and a lot of loop optimizations and profile guided optimizations are conducted because of this. Here in this chart, you see that it has wide range of applications across vision, NLP, and these are the two major DL frameworks which we work on. And we are contributing to the oneDNN for ARM CPUs. This is the part which we are tuning and enabling. So in this field, one of the biggest contributions from Fujitsu in recent time has been BRGEMM matrix multiplication enablement. And this expands our scope of matrix multiplication, more efficient matrix multiplication for the deep learning workloads. What is BRGEMM? It is batch reduced journal matrix multiplication. These are the tensors reduced into batches for multiplication. Then the broadcast happened for all these input values. And then we perform FMA instruction, which is a fused multiply add instruction at once for all the multiple batches. And with this change, we have observed almost 9 to 10x performance gain compared to the oneDNN GEMM JIT implementation, which is a reference implementation. So this is the improvement which we have seen with this optimization. Next, which we are working on is JIT kernel expansion across multiple ISAs. So the most recent has been softmax kernel, which we have expanded to support for multiple ISAs. And for this support, there are primarily 3 layers which are modified for this primitive. The implementation is done for the multiple ISAs. Then the second is the prioritization is set up, that how will the kernel prioritize which ISA should be used and in what sequence. So the conditional statements were added and new functions were added supporting SVE for different vector lengths. And these are the performance results which we have seen. And we are comparing on these 4 metrics, the ACL, SVE, reference, and AVX. And we see good performance compared to the reference kernel implementation. And similarly, we did the pooling kernel implementation for multiple ISA support. And in addition to the 2 changes which were done for softmax, like the conditional statements and the implementation, we have also added modified the load and store instructions to use the predicate registers for the correct ISA matching. And this is required especially so that we are utilizing the vector lengths correctly and optimally. With this change also, we are seeing very good performance boost compared to the reference implementation. And this is one of the kernel which even beats the ACL performance for the kernel implementation. So this concludes the DL deep learning contributions from Fujitsu on ARM. So all this work we are doing, our department is focusing on the next generation ARM-based CPUs called FUJITSU-MONAKA. And this, we are developing a new power-efficient CPU for data centers, which will be shipped in 2027. And this image on the top left you see is the Japanese suite called Monaka, and our project is named on that. With that, our vision is that the software stack should be as sweet as Monaka, so that it is able to run on any workloads. And we are targeting wide usage of this CPU for the data center operations, including AI and HPC. And with this, we are focusing on both the fronts. the hardware innovation which is being conducted in the Japan office, and we are focusing on the software side in FRIPL, and we are focusing on all the application performance with all these features of high performance and energy efficiency, and how do we make it easy to use. And that is one of the primary reasons of collaborating with Linaro and with UXL Foundation, and we are working very closely with the ARM open source community, because we want to make sure that the CPU, when it comes in the market, it is able to cater to any workloads in the industry. So these are the 4 fronts which we are currently working on. So we continue to work on the ML acceleration techniques by doing more algorithmic improvements, kernel improvements. Then on the oneDNN side, we are expanding it with multiple JIT kernels. We are also utilizing BF16 data types in the optimal way. We are working on the GEMM-based convolutions. And then our vision is that we want to accelerate the software performance on ARM for FUJITSU-MONAKA. And there's nothing proprietary happening. It is all open source. And we are working on multiple fronts, like real-time data processing, big data analytics, and data security, NLP, and LLMs, and GenAI, all the fronts which we are working on. And with this, we want to make sure that the software is ready for FUJITSU-MONAKA. And last, we welcome your feedback and your collaboration on any of the open source projects which Fujitsu is working on. These are all the resources which we have added in the slides for reference. And this also has references to FUJITSU-MONAKA introduction and the press releases. And these are all the pull requests which we just shared. We acknowledge all the support and collaboration which we are doing very closely with Japan teams. And we are working together as one team. And this project is all the results, all the work which we are doing, all the contributions are part of the NEDO Project, which is a national research and development agency in Japan. It is a new energy and industrial technology development organization. And Fujitsu is participating in these efforts and contributing all this work which we are conducting. Thank you. Thank you, everyone. Thanks for listening. Any questions? Take the mic.
Thank you. So I want to ask, in the 2027 years product, do you have the SME extension support? So in the pull requests you explained, I didn't hear much about the SME extensions. So is there any plan for that? For the new instruction matrix instruction sets?
Yes, thank you for the question. So currently, for Monaka, we are only focusing on the SV optimizations, not yet for SMEs. But at the right time, we'll definitely explore it. But our first goal is to make it happen for the SV optimizations only. We are not targeting currently for the SMEs. Thank you. Yes, please. You can take the mic. Thank you.
First of all, thank you for this great contribution to OpenBLAS. It's awesome. My question is, during the port to ARM64, what was your definition of done, let's say, some kind of test suite or benchmark to assure functional completeness?
Yes, so we are definitely working on taking milestones and completing, but maybe these kernel optimizations are never done. So as of now, we are comparing it with the reference backends. We are making sure that in the ARM ecosystem, those kernels are performing the best. And that is our benchmarks which we are currently targeting. So as of now, we are testing all these softwares for Graviton3 and Graviton3E machines, and Graviton4 is also coming up. So we are testing all these softwares on those and making sure that it runs the best for the ARM ecosystem. That's the first benchmark which we are testing. Thank you. Yes.
Hi. All of these contributions to OpenBLAS are very welcome. Do you feel that you're getting enough support from the ARM team, in particular the ARM Performance Libraries team?
Yeah.
Because I expect that in most cases, at the moment, ARM Performance Libraries should have the most optimized versions for Neoverse V1 for the kernels that you're working on in OpenBLAS. And I'm not suggesting that you stop using OpenBLAS, but whenever you're doing optimization work, it's always useful to have an oracle of knowing how much more potential there is for each kernel. So are you comparing against ARM-PL at the moment?
Yes, thanks for the question. So definitely we are comparing all the OpenBLAS performance with ARM-PL. We are in close contact with the ARM team, especially Chris Goodyear's team, and Ashok Bhatt, who is the project manager in India. So we work very closely with them. We are in discussions about the latest release of ARM-PL, and it has OpenRNG, and we have started discussions with them of how we can collaborate on that, and how few of the missing kernels and few of the optimized kernels can be upstreamed there as well. So we are working on both the fronts definitely, and we are in close collaboration with ARM team on utilizing
So
ARM-PL as well.
You're speaking to exactly the right people, so that's perfect.
Thank you so much. Thank you.
Hi, I'm with Leonardo, working on a project that needs optimizing for SV as well.
Okay.
So I'm wondering, what's your experience of scalability and using multi-thread on different hardware? So, for example, if you've got 96 cores, can you actually scale up to 96 cores without the synchronization getting in the way?
Yeah, so the parts which I mentioned about the multi-threading scalability, those are few of the initial contributions from our side, but there's still a lot of scope of work to be done, and we are continuing on that front. So we are utilizing from both native kernel implementation as well as the SV optimization perspective, both the fronts. And we feel that there's still a lot of work to be done, and definitely if Leonardo is also interested on that, we can collaborate. But yes, these are just the initial contributions, and there's still a lot of scope to be done. Yeah, so even in thread composability subject, which makes the backend much composable with the threading backends, that is very important from the scalability perspective, especially for the processors which are large core like MONAKA. So definitely we are working on that, and we can collaborate with Leonardo. Thank you.
We have previously worked on the OpenMP runtime to improve scalability for earlier ARM cores. We're not actively doing anything at the moment, but if you find any scaling issues, we're happy to help, so let us know. Yeah, there were the OpenMP runtime at the time we looked at it, it's maybe 5 years ago, had some fairly fundamental software limitations on how well it scaled above. I forget the number, but it was the maximum number of cores you could expect to find on an x86 machine at the time. So we made some improvements there. But anyway, if there's anything you feel we can help with, then we're happy to.
Yes.
So my question was also around OpenMP. What OpenMP library did you see problems with? Was it LLVM or GNU or something else? And why? And was it difficult to implement your own thread pooling solution?
Yeah, we had few discussions internally of whether we should go for new threading implementation, but as of now, we are not looking for any proprietary solutions. We are only looking at open source. We are trying to work on how best we can utilize the existing threading backends. So we are exploring OpenMP, pthreads, TBB. Even Julia has a threading backend called Parter, which we are exploring. So all these threading backends, we are wanting to make sure that they are composable with OpenBLAS, so that based on the type of the workloads which come in, we can suggest which threading backend would be the most suitable. And the OpenMP version which you mentioned, so we are looking at the latest OpenMP versions only. And so wherever we find any bottleneck, so there's still a lot of difference between OpenMP implementation and the pthreads, and maybe they are meant for different types of implementations. So we are looking at both the fronts. I don't know if it helped to answer, but yeah, you can maybe repeat.
I'm from the linear
Comparison.
toolchain team, which works on LLVM and GNU, and
Yeah.
I was wondering whether you saw the problems in OpenMP's, in GCC's OpenMP implementation or in LLVM's OpenMP implementation.
Yeah, so currently we are testing on the default, which is sometimes few backends are on GCC, sometimes on CLang, but we are primarily focusing on the LLVM side. And these results which we are showing, they are primarily on LLVM. Yeah. Any other question? Okay, thank you everyone. Thanks for joining.